Okay, so yeah, so I guess I wanted to start off by just recapping method of steepest descents real briefly. And just kind of summarize that the main idea is that you're going to start by looking to deform the contour, okay, of your integral, right? So let's say, just to remind us, right, the kind of integral we're talking about. I of x equals some integral.
I'm getting the skinny white rectangle.
Oh,
yeah, me too.
That's good.
Yeah. Sometimes it doesn't tell me when that's happening. Okay. All right. Is that visible now?
Yeah, that's good.
All right. So if we have some integral like this, where x is large, the idea is that we're going to look for saddle points, okay? And then we want to deform, we want to look for saddle points of this function and deform our contour to be the steepest descent contour through relevant saddle points of rho of t, okay? Now, it may be that you don't have any relevant saddle points, in which case we'll explain what to do. But if you do, you want to evaluate the local contribution from the saddle as in Laplace's method. So that's the idea, is that you draw a contour through some point so that your real part is going to, allow you to get an integral over a Gaussian, and then that will be your leading order approximation. Now, the other thing is that if you have some, integral that's over some finite interval, you're going to have endpoints, and you have to deal with those, as we did in the example that I sort of started on Monday, and then I redid on YouTube. So the idea is to evaluate the local contribution from the endpoints as in Laplace's method again. So you want to use the steepest descent direction also from the endpoint, okay? And the key idea here, in order to get the steepest descent direction, is that you want the imaginary part of rho of t be equal to the imaginary part of rho of, let's say, t0, right, where this is your end point for saddle. And you want your real part of rho of t to be less than 0 in this case, and ideally as small as possible, okay? So these relations will allow you to write down the parameterization of the contours that you would want. It often helps to sketch these out, as we've done for these examples. And in the case of the homework problem that I gave, just want to briefly remark on that. The homework problem that I gave, so this is problem 1 on homework 3. we'll just kind of give a couple hints. The integral that you end up trying to evaluate, you can change variables and write it like this. Okay. E to the minus r squared u squared du, where z is equal to r e to the I theta. Okay. So now your thing that was large in amplitude was z, but you've changed variable so that you just have the amplitude. So now r is the thing that's large in this case. If we sketch out, right, for a particular value of theta, and in the problem they tell you to sort of start with theta is somewhere between minus pi over 2 and pi over 2, then this is what your contour looks like, okay? And so the idea is that you have to figure out where to draw a contour from here and where to draw a contour from here. It's not hard to show that this is a saddle, right? Because this is going to have derivative, your rho function up here is going to have derivative 0 at 0 in this case. But you also have to deal with this endpoint as well. So you're going to have two contours, okay? And the key here is that, and this may help you some, if you start at u equals I theta, that's going to give you the best clue as to the direction that this contour should go from here. And so the idea is that in that case, right, we take the imaginary part of minus u squared, right? Because now, you know, your thing that's big is r squared. You could write that as, you know, x or something like that if you like. Okay, but the imaginary part of u squared in this case needs to be equal to the imaginary part of e to the I theta, which is equal to sine of theta in this case. And if you write u in terms of Cartesian coordinates, u equals x plus I y, then you actually end up with sorry, made a small mistake here. We've got 2 there. Okay. If you write this in terms of Cartesian coordinates, I need a minus sign out there, and I need a 2 right there, then you end up with 2xy minus 2xy, I guess, equals minus sine of 2 theta. Okay. So this now is your steepest descent curve in Cartesian coordinates, right? So y is equal to sine of 2 theta over 2x here. And because they both start positive, right, we need that x and y are going to be positive in this case. Okay. So that suggests that you have this contour here that runs in this direction. And that should give you a clue as to what direction you might have to take from the saddle in this case. All right. So I know, yeah, maybe you haven't looked at this problem yet, but I just wanted to give you a nudge in that direction because I know that, yeah, there's a lot of different things that you can encounter with steepest descent. So a lot of choices to be made. So I would say, you know, start with this endpoint here, okay, and then, you know, use your the imaginary part has to be constant, emanating from that. Okay, you can also apply this principle as well, right? But you'll get the same contour as you would from just using the imaginary part. Okay. All right.
On the first page, could you say what it says? It says something or saddle on one of the lines, but I just wasn't sure what the first word was. Right above imaginary
Endpoint.
row of TZ.
Endpoint.
Endpoint
right.
or saddle. Okay.
Yeah. So if you have these finite finite contour integrals, then you need to make sure that you have a way of joining back to the original contour here, right? And so you want to go steepest descent away from the saddle here, but then you want to sort of loop back, or you can draw the contour any direction, and then you use Cauchy's theorem to make sure that you've gotten the signs right in terms of those. And the hint here is that basically either the saddle integral, the one emanating from the saddle, or the non-saddle endpoint, so that's what I mean by endpoint integral, will be the sole leading order integral. Okay. So that's what you're supposed to explore in this problem by looking at, different values of theta. The leading order of this is going to change, and also potentially the direction of steepest descent is going to change. And so you just have to figure out how the steepest descent direction and this leading order behavior changes as you vary that angle that you're drawing the contour for your integral along. Okay. All right. So I think that's pretty much it for steepest descent. You'll tackle that problem on this homework that's due in a week. I'm going to move on to ODEs now. Okay. So let's switch gears a bit. The idea now is that we have to worry about functions having perturbation expansions or asymptotic expansions, but also their coordinates having asymptotic expansions. So these are the types of things that come up when we deal with asymptotic solutions of ODEs. Okay, we're going to talk a lot about what's called matched expansions, where maybe you have one expansion that works in one region that your ODE is defined on, and then you have another solution that's maybe defined on a skinny region, maybe close to a boundary, although it could be internal as well to the domain. Okay. So we have to talk first a little bit about coordinate expansions. Okay. We have typically use things like f of x is much less than g of x, okay? But you could have f of x is approximately given by g of x as x goes to some value x0, okay? So parametric expansions, right, might not be in our variables, but they might be in some parameter that determines our equation that we want to apply asymptotics to, okay? And so if we have this big O notation, the limit as epsilon goes to 0 of f of x epsilon divided by g of epsilon should be a constant that's less than infinity in that case. And typically we can only make this claim for x fixed, okay? But if this holds for all x in some domain, a, b, f of x epsilon is equal to some big O of g of epsilon, okay, as epsilon goes to 0. Then we say this holds uniformly in X, okay? And for ODEs, we're going to look for cases where asymptotic expansions are valid uniformly in X, because we need these functions to work as solutions over a wide range, okay? So the same holds for little o notation. You can also define uniform little o notation, right? F of X epsilon equals little o of G epsilon as epsilon goes to 0, uniformly in X on A to B if the limit as epsilon goes to 0 of F of X epsilon divided by G epsilon, if that is equal to 0, basically independent of X, okay? So, so we have, several things that work here, right? When we're dealing with ordinary differential equations, we have the parameters, we have the coordinates, and we also have the functions of interest. And all of these, we're going to potentially have to play games with what asymptotic expansions we use, okay? And so I'll just remind us that asymptotic sequences, okay, they have the property that for some asymptotic sequence phi n of epsilon, going from n equals 0 up to infinity, is an asymptotic sequence, okay, as epsilon goes to 0, if phi n plus 1 of epsilon is much less than phi n of epsilon. Okay. That's horrible, horribly squished there. Let me rewrite that. Okay. So we've written that down before, right? Now we're talking about applying this to functions and potentially their arguments. Now, the other thing that we talked about in algebraic expansions was the difference between regular and singular expansions. And regular expansions are your typical kind of, they could be a power series or they could be an expansion in some, sort of exotic transcendental function. But the idea is that they don't really, their sort of behavior is predictable as epsilon goes to 0, okay? So for some asymptotic expansion, let's say f equals this weighted sum of this asymptotic sequence as epsilon goes to 0, okay? This works as an asymptotic expansion if and only if f of x is equal to sum from n equals 0 up to some n, an of x phi n of epsilon plus little o of a n of x phi n of epsilon. Okay. Uniformly in X again. Okay. This is any expansion, Now the expansion is going to be regular if a and phi, a n of x, phi n of epsilon is much less than a n minus 1 of x, phi n minus 1 of epsilon. As epsilon goes to 0, again, uniformly in x, okay? On the other hand, if a n of x, phi n of epsilon equals big O of a n minus 1 of x, phi n minus 1 of epsilon, where epsilon goes to 0, for some range in x, then the expansion is singular, okay? So this means that singular expansions, they're going to break uniformity, and this region of non-uniformity essentially we need to solve the quote equation a n of x phi n of epsilon equal to big O of a n minus 1 of x phi n minus 1 of epsilon for that range of x, and obtain how x is equal to some function of epsilon in that case, which we'll call delta, okay? So this is building up to something that we'll call matching. So essentially, if you have some singular region, then we need to kind of deal with that particular region differently, that non-uniformly converging region differently. And it's essentially change coordinates in order to separate out an outer region potentially from an inner region, which we'll get to, okay? Now, the way I'm going to structure this kind of the next few lectures is mostly that we're going to go through some examples. This is kind of following the Holmes book, which is in Canvas. So you can follow along there, and there's some additional examples as well. But mostly we're going to see what happens in these different situations in ODEs when you have this region of non-uniformity at different places in your domain, okay? So just to start with, let me look at a linear ODE problem. And we're going to take the equation y sub tt plus y is equal to epsilon y for t greater than 0. Epsilon is small, okay? And some initial conditions, y of 0 equals y sub 0, y sub t of 0 is equal to v sub 0, okay? Now let's start with doing some sort of regular perturbation expansion, okay? And you did this, you know, kind of on the first homework you applied to a problem like this, right? So your first intuition may be to say, well, let's say that yt of epsilon is equal to some function y0 of t plus epsilon y1 of t plus epsilon squared y2 of t, and so on, as epsilon goes to 0, Okay. Now this is going to work for some problems, right? But in order for it to work, you need this to be a uniform expansion. And that's the case if what? Well, if yn of t is equal to big O of 1, or t greater than 0, as epsilon goes to 0, okay? So we can now see immediately maybe where a regular perturbation expansion might foul up, right? If any of these solutions blows up at some point, you lose this uniformity assumption, right? So this is going to happen in one particular situation to get this non-uniformity is, let's say if you have something like resonance, right, in your solution, and you have just growing oscillations that grow exponentially. Could just be pure exponential growth or something like that. So that puts a bound on the region maybe where a regular perturbation expansion is valid. So you may have to sort of block off regions in time where that approximation is going to work okay. Okay. So let's see what happens here. So if we substitute,
Do we have two different y zeros here? Like, is the initial condition different than the first one in the expansion?
Oh yeah. I realized what I did in my notes. I sort of crossed something out. So I'm going to use I'll use superscripts for the initial condition. I did that in my notes, but then I forgot that I did that here, and I just thought that I was crossing something like that. So let's use superscripts for the initial condition. Okay. Subscripts will be the index of the elements of your regular perturbation. Okay. So if we substitute and equate our like powers, right? So you just take this expansion, you plug it in, you look for the order 1, the order epsilon terms, you start climbing up the hierarchy. At order 1, what we're going to have is y0 prime prime plus y0 equals 0. That's it, right? That's the only order 1 stuff. We can solve that. Okay, let's write out the complex exponential version of that. So we get a0 equals e to the I t plus a0 star e to the minus it there. At order epsilon, we have y1 prime prime plus y1 equals y0. Okay, so in this case, right, we know that a0 is equal to a0 e to the it plus its complex conjugate. So then y1 of t, if we just look for the particular solution, so let's ignore the homogeneous solution. Why would we ignore the homogeneous solution? Well, that's just going to be just adding to the solution from before, right? That would just change this coefficient. So just to look at what happens with the particular solution, we see immediately that we have a resonance here, right? And some complex conjugate terms here. So moreover, if I compute y1 prime, right, I'm going to get a1t plus I a1t e to the I t here plus complex conjugate. And then if I look at y1, its second derivative, then I'm going to get 2i a1 minus a1t times e to the it plus the complex conjugate. Okay. So we're just doing undetermined coefficients here. We can insert our ansatz now, and we'll specify what A1 is. Okay. That's not so much the point what A1 is. The main point is we have this resonance now, which is going to have us run afoul this regular perturbation expansion at some point. So if we insert our ansatz, right, we can get 2IA1 minus A1t e to the it plus A1t e to the it, okay, plus their complex conjugates, right? Plus CC plus CC, right, is equal to A0 e to the it plus complex conjugate, okay? So this implies that 2I A1 is equal to A0. In other words, that Y1 is equal to minus IT over 2A0 e to the it plus some complex conjugate, okay? Now we can do this all the way up the hierarchy, right? And we'll get yn prime prime plus yn is equal to yn minus 1, okay? We just keep swapping these things in and out. And it turns out you get more and more higher powers of t out in front, okay? So I'll just sort of write the first few terms for you, what happens here. You could do this. It's just sort of plug and chug and some more and more annoying algebra, I guess, as things go along. But you get A0, 1 minus epsilon IT over 2, and then minus epsilon squared. You get a p squared plus IT to your next term, and so on, all times e to the it plus some complex conjugate. Okay. Now, our ODE, we wanted to define it on t goes to infinity. Okay. So what happens as t goes to infinity, right? We want to capture the whole domain of t greater than 0. Okay. Well, the issue is here, and that's really the point I'm trying to make here, is that our asymptotic ordering is going to break down. Okay. And so overall, it's only going to be valid for order 1t. Okay. And at t equals order 1 over epsilon. Okay. And then we have that epsilon y1 is going to equal order 1. And we essentially get non-uniformity of our asymptotic expansion. Okay. Now there's a lot of ways that non-uniformity can crop up. This is just one of them, right? This is a resonance example, and we'll circle back to this later. It's a little bit trickier to deal with than other types of non-uniformity, okay? But it's kind of easy example to demonstrate, okay? So that's kind of all I want to say about this example for now. We'll circle back to it later. And then we're going to start to unpack some examples where non-uniformity occurs in other ways, okay? Any questions so far about this? All right. So the key is, we want expansions that maintain uniformity, okay? Now for that example, we would need to introduce additional terms to basically remove our secular terms, okay? And this is sometimes called the frequency shift method. And we'll talk about that later, okay? Now, another way that you could get non-uniformity, okay, in solutions to ODE, okay, is that you may have what are called boundary layers, right? So our example that we just showed, right, where we had, what was it, y prime prime plus y is equal to epsilon y, right? We had these solutions that were kind of growing like this over time, and the non-uniformity starts here, right? Now for boundary layers, what we find, okay, is that we have to resolve them by what are called matched asymptotic expansions, okay? And this is kind of the content of Holmes' book 2.1, 2.2, which we'll pretty much go over here, although I won't go through the whole guts of all the examples that he goes through, okay? But the idea with a boundary layer might be that you have some equation, right? Some ODE on T, and here's your Y, and your region of non-uniformity happens right at the boundary, okay? But then your outer region here is fine, okay? And essentially you may have, some Y here, but then when you get into this region, right, Y is starting to shoot up, right? And maybe it has a very sharp derivative or something like that, okay? But the way that the terms get ordered, either in the differential equations or your asymptotic expansions, is not consistent with the outer region, okay? So, so remember, there's these two sort of classes of perturbation expansions, right? Regular perturbations can handle epsilon multiplying linear order derivatives, okay? Or sorry, lower order derivatives. Read my own writing. But you may have a differential equation where you have epsilons multiplying your highest order derivative, okay? And for that, you need singular perturbations, okay? Right? So this is not that far off from what happened with algebraic equations, okay? You remember the quadratic equations that we solved. When the epsilon appeared in front of the x squared term, then that's when singular perturbations were needed. If it multiplied the lower order terms, then that, you would only need regular expansions for that, okay? So the idea here is that singular perturbations, right? You can get boundary layers in either kind of problems, right? But the other choice that you have to make is whether you, construct regular or singular perturbations, okay? Because essentially the fundamental structure of your solutions is going to change as epsilon goes to 0 if epsilon is multiplying the higher order derivatives, okay? So let's start with a linear example. I think we'll be with this example for the rest of class and then into the next class, okay? We're going to write down a fairly harmless looking ODE here. It's just a second order ODE, okay? And I'm going to define some boundary conditions. So y0 equals A, y1 equals B, and B epsilon is going to be our total problem here, okay? And the version when epsilon equals 0 will be our D0 version, okay? It's just what I'm calling these two different differential equations, right? So the limiting case here is fundamentally different than the epsilon greater than 0 case, okay? Now, what usually happens when you go to leading order is that you can just take epsilon to 0, and then you sort of expand around that if you're using kind of a standard regular perturbation type argument. So in this case, if I just solve the D0 equation, okay, it's kind of weird because, if you think back to differential equations, I have a first order equation, but I have two boundary conditions, okay? And that's going to be a problem because in general, I could not expect to be able to satisfy two boundary conditions if I have a first order differential equation. And so y equals a e to the minus x, I only have one free constant, okay? So I can't satisfy both boundary conditions in this case, right? Now, if y solves the epsilon now, okay, now I can maybe start to piece together other functions that would satisfy both of these boundary conditions, okay? And often, okay, in general, right, we might have this situation where epsilon times the kth derivative of y is small, and y approximately obeys D0 almost everywhere, okay? So you can maybe start to see here what these sort of boundary layer matched asymptotic type solutions might look like, right? In most places in my domain, I may have a solution that kind of looks like this leading order solution, but then in order to satisfy the boundaries, I may need to glue it to a solution that satisfies the boundary condition, okay? So I need some systematic way of doing that, okay? And so basically in certain regions, and often this can be the endpoints of your domain, right? Although, for instance, right, epsilon times y kth derivative is not small, okay, and adjusts for our boundary conditions, okay? And like in our example here, right, we may have our solution here in our outer layer, okay? But then in the boundary layer here, something may happen like where I have to take another function, or I may have to use a different expansion in this boundary layer in order to satisfy this initial condition, or sorry, this boundary condition y0 of a, and then I might also have to do that in this boundary region here, right? In order to satisfy this boundary condition here, y1 of b, okay? So these are called boundary layers in fluid dynamics, call them edge layers in solid mechanics. In electrodynamics, sometimes we call them skin layers, but because the fluid dynamicists, sort of dominated this, we just call everything kind of boundary layers. So the idea is that to solve this, okay, we're going to take the following steps, okay? And let me start this on the next page, actually. I have a little list here, okay? Now to solve this issue, right, we have to do a few things. First of all, we have to determine the scaling of the boundary layer, okay? In particular, is X going to be, is it going to have scaling like epsilon or epsilon to the 1/2, right? So on. Secondly, we're going to have to rescale then that independent variable in the boundary layer to match that scaling that we identified, right? So in that case, we might use X equals X hat times epsilon, or X hat times epsilon to the 1/2, right? We just make a change of variables that's matched to the scaling that we do, okay? The third thing that we do is that we'll find this outer solution, and we already identified the outer solution for that example problem that we talked about, right? It's just that exponentially decaying function. So that's going to be most of our domain, okay? And then we find the inner solution, and that's going to live in our boundary layer, okay? Now, it doesn't always happen on the boundaries, and it isn't always necessarily the function itself. It could be the function's derivative, in which case you might have an interior layer, you might have what's called a corner layer, and we'll look at those in future lectures as well, okay? And then once you have the boundary layer solution and the outer layer solution, okay, or the outer solution, you need to figure out how to piece these together, because you want a solution that you can write down as an expansion where essentially everything sort of smoothly runs into each other at these the junctions of these boundary layers and the outer layers, or the outer solutions, okay? So we're going to end up with a bunch of constants, and those are going to sort of allow us to fix our interfaces between the boundary layers and the outer solution, okay? So in general, for boundary layer problems, the inner solutions are going to obey the given boundary conditions of the problem, okay? And then we're going to have this sort of matching region, okay, where the inner and outer solution sort of get stitched together, okay? And so this might be like, you know, I have my inner solution here and my outer solution here, and we're gonna tune constants so that we match those together. And this is then called our matched asymptotic expansion method, okay? And the idea is very generalizable, and we can climb up the hierarchy. So typically you're only going to do this to like leading order, or maybe, you know, second order or something like that. But you can keep carrying this forward, you know, across higher and higher order expansion, okay? Typically leading order is going to be good enough, and so that's what we'll stick to with kind of most of our problems that we'll go through, okay? So that kind of motivates the couple of problems that are on the homework. On Friday, we'll go into more detail, and that'll kind of sketch out for you what you'll need to do on those particular problems. So this is matched asymptotics for ODs. Any questions about this? All right. Cool. All right. Well, yeah, just a reminder, your next set is due on Wednesday. The deadlines are now shifted to Wednesday, every 2 weeks, basically, from now on. Yeah, let me know if you have any questions about the problem set. Otherwise, I'll see you on Friday.
Thanks, Zach.
Thanks.